So we're going to look at one more example, put together one more set of tools to solve problems involving circular motion before we move on to something that's a little bit different. So let's remember the relationship between frequency and period. This is 20 RPM. What is the frequency and period of 20 RPM? Okay, RPM is rotations per minute or revolutions per minute, depends on what you're talking about. And so the thing that we need to fix here is the per minute part, because the frequency is measured in hertz, which is cycles per second. So our problem here is that 20 RPM is cycles per minute. And so we really need to change that into cycles per second. So 20 RPM, let's call it revolutions. And I want to change that to per second. Now you may be able to just mental math that, but let's do it using the good old-fashioned unit conversion method that we learned so long ago. 1 minute is 60 seconds. So we're doing 20 divided by 60, right? Because the minutes cancel each other out. And so we end up with revolutions per second. So 20 divided by 60 is 1/3, or 0.33 hertz, or cycles per second. So that would be the frequency. And then we want to figure out what's the period. So this is easiest to do using this fraction over here, right? Because the period, which is actually denoted with a t, is equal to 1 over the frequency. And so that gives us 3 over 1, which is equal to 3 seconds. And that is our period. So the frequency is 1/3, so that means that 1/3 of a rotation or revolution or whatever we're talking about, cycle, happens per second, and that means every rotation, revolution, cycle takes 3 seconds. That's just an important thing to remember how to do. And then we come to our final question. This has nothing to do with the frequency and period thing we just did. That was just an important note to keep in mind for the practice you're doing later. A 1,600 kilogram car is traveling around a curve with a radius of 500 meters. The road is banked at 15 degrees. What is the maximum speed of the car if the coefficient of friction is 0.21? Okay, the fact that this roadway is banked changes everything. Well, not everything. It changes how we should think about this a little bit. So, banking the roadway at 15 degrees, this is far more than 15 degrees, but let's go with it. Here's our car. It's a box. Believe it or not. And so let's draw the forces in here. We've got the force of gravity pulling it straight down. We've got the normal force. I've got to tilt my head to draw this correctly. We've got the normal force pushing perpendicular to the roadway, perpendicular to the slope. And then what else do we have? Well, it gives us the coefficient of friction in the question, so that should be a clue that we're going to include friction in this thing. The question is, which direction is friction pushing? So let's just imagine if there was no friction, what would happen to the car? So the car's driving around the curve, and suddenly the friction is gone. What happens to it? Well, it slides up and over the curve, right? So it first of all, it stops being able to turn. It also stops, it now slides up the curve and over the embankment, probably. And so friction is keeping the car moving in a circle. So our force of friction is actually going to be that direction, along the roadway. Okay? So now the question here is, what forces are causing this vehicle to continue moving in a circle? We know that friction is going to be one of them. Gravity is not in the direction that we would expect it to be in this case. For an inclined plane, yeah, this is all perfectly normal. But when we're talking about the centripetal acceleration is toward the center of the circle. Okay, and so that would be this direction. And so we need the component of gravity that's parallel to the roadway. So we're going to do this. Split it into components. Oh, isn't this beautiful? We're combining inclined planes with centripetal motion. It's really just beautiful. This is FGY. This is FGX. So we need FGX because it will be part of centripetal force. We also need FGY actually, but only to calculate the force of friction. Okay, so when we figure out centripetal force, it's mv squared over r again, and we need to make sure that we split the centripetal force into only the pieces that are actually involved in that centripetal acceleration. So the normal force is not going to be one of the forces involved here because it's perpendicular to the motion. Okay, it's not involved at all. And so when we split centripetal force into its pieces, we know that the force of friction is going to be one of them, and the force of gravity X is going to be one of them. Those two things together are going to contribute to that centripetal acceleration. So now we are going to have to expand these two parts of centripetal force into their formulas. Okay, so force of friction, I should put vector symbols on these things. The force of friction is the coefficient times the normal force. The force of gravity X, if this is 15 degrees, I'll write that in here, 15 degrees, uses the sine, right? So it's mg sine 15 degrees, and together those things equal mv squared over r. I am trying to solve for v. Okay, so when it's asking us for the maximum speed of the car, this would be when our centripetal acceleration allows the vehicle to go around in a circle. Any speed greater than what we calculate right here would require a larger force of friction or a larger FGX. Okay, so when we calculate this v, it is giving us the maximum speed that can be sustained with these conditions. So I'm trying to solve for v. So I'm going to multiply by r, and I'm going to divide by mass, and I'm going to square root the whole thing. Okay, so here we go. Here's our new formula. Well, how about this? I'm going to expand the normal force into its formula as well, and then we'll do all of that stuff. So here's the coefficient times mg cosine 15 degrees plus mg sine 15 degrees equals mv squared over r. And now we can see again that the mass isn't actually required, which is what we saw in the previous example as well, if you watched the previous video, that when you design a roadway, you don't actually need to take the mass of the vehicles into account, right? So we can cancel out all those masses. Now I'm trying to solve for v, so I need to multiply all of this stuff by r and then square root it. So here's where I'm going to do that. So this is the square root of the coefficient of friction times the cosine of 15 degrees. Times g, shouldn't forget that. Plus g times the sine of 15 degrees. Multiply all of that by r. And square root it. And that gives me v. Okay, now the coefficient is 0.21. G is 9.8. And so when I plug all of this in here, Oh, and I should say r is 500 meters. When I plug all of this in here, you should get a maximum velocity of 47.6 meters per second.